Here we look at a couple examples of partial fraction decomposition of improper rational expressions, okay? Improper rational expressions means that the degree of the numerator is greater than or equal to the degree of the denominator. I'll say that one more time. The degree of the numerator is greater than or equal to the degree of the denominator. And if that's the case, the very first thing we have to do is divide. We must complete polynomial long division to rewrite the rational expression so that it is no longer in improper rational expression form. So to complete our polynomial long division, we take x squared, we put that inside of our long division box, we put x squared minus 1, our divisor, on the outside. We are dividing x squared by x squared minus 1. To do this, we look at the first term here of our divisor, and we say, how many times does x squared go into x squared? In other terms, what do I have to multiply x squared by to get x squared? Well, the answer there is 1. So we put a 1 up top, and now we multiply 1 down to our divisor and distribute. 1 times x squared minus 1, that gives me x squared minus 1, and working vertically in long division, we subtract. X squared minus x squared, those are going to give me 0. I've got 0 minus a negative 1. Subtracting a negative 1 is the same as adding 1, leaving me with 1. Next, we check to see, how many times does x squared go into 1? What do I multiply x squared by to get 1? Well, that's not going to work out. X squared does not go into 1. That tells me that 1 is the remainder of my polynomial long division. And my solution, my quotient to taking x squared and dividing by x squared minus 1 is equal to 1 plus 1 divided by x squared minus 1, right? We take this value up here, we add on the remainder divided by our divisor. The remainder was 1 divided by the divisor. Okay, so we completed step number 1, our polynomial long division. Now we want to decompose this fraction. So we're going to be working with just the fraction, the rational expression 1 over x squared minus 1. All right, again, this is what we just did. X squared over x squared minus 1 is equal to 1 plus 1 over x squared minus 1. To decompose the rational expression here now, we need to factor the denominator. The denominator of our fraction factors into x plus 1 times x minus 1. We recognize that these are distinct linear factors. Distinct linear factors decompose or break apart into a constant divided by each factor. In this case, a over x plus 1 plus b divided by x minus 1. To complete the partial fraction decomposition, we must solve for the constants a and b. This means we need to multiply by the least common denominator, and the least common denominator, as we have seen before, is the denominator of our original expression, okay, the fraction we were trying to break apart, x plus 1 times x minus 1. Well, when I multiply the left-hand side of the equation by x plus 1 times x minus 1, the whole denominator here gets canceled out, and we are left with 1 is equal to a times the x plus 1s will cancel. We are left with a times x minus 1 plus b over x minus 1 times x plus 1 times x minus 1. The x minus 1s cancel, and we have b times x plus 1. 1 equals a times x minus 1 plus b times x plus 1. Now we can distribute and expand. We multiply the a and the b through. We get 1 is equal to ax squared minus a plus bx plus b. We group our like terms. We're going to group our x terms together. We get 1 is equal to ax squared plus bx minus a plus b. And now we can factor out our common factor of x from this first grouping here. That leaves me with a plus b, the quantity a plus b times x, minus a plus b. And that all has to equal 1. So at this point, we know that the coefficients of all of the x values on both sides of the equation have to be the same, as well as the constant terms. Well, on the left-hand side of the equation, there are no x values. In order for this to be an equation, I have to have no x values on the right. I have to have 0x. Well, in order to have 0x, that means the constants a plus b must equal 0. A plus b is equal to 0. The constant on the left-hand side of this equation is 1. Negative a plus b is what is going to generate the constant on the right-hand side of the equation. That means negative a plus b must be equal to 1. And here we have just created a system of equations. Now we could solve this one using substitution or elimination. I use substitution where I isolated a here. A is equal to negative b. I can now substitute that into my second equation. That gives me negative 1 times negative b plus b equals 1. Negative and a negative, when I multiply those, they give me a positive. B plus b is 2b equals 1, which means that b is equal to 1/2. And if b is equal to 1/2, I can back substitute that into this equation here, leaving me with a is equal to negative 1/2. All right, now that we've solved for the constants a and b, we are ready to write our final answer. I always recommend starting off with the original expression. X squared divided by x squared minus 1 is equal to. What did it break apart into? Well, don't forget about this 1 to start off. It broke apart into 1 plus, and then we split up this fraction, 1 over x squared minus 1. And what did it split up into? A over x plus 1 plus b over x minus 1. X squared divided by x squared minus 1 is equal to 1 plus negative 1/2 over x plus 1 plus 1/2 over x minus 1. Now, we almost have a final answer here. The only thing ugly about this is our complex fractions. So we simplify these complex fractions. This denominator 2 ends up in the denominator of our fraction. This denominator 2 ends up in the denominator of the next fraction. We can, instead of adding a negative, just rewrite adding a negative as subtraction, giving us our final answer. X squared divided by x squared minus 1 equals 1 minus 1 over 2 times the quantity x plus 1 plus 1 over 2 times the quantity x minus 1. And if you were to combine all of these terms together by getting a common denominator, yes, you would end up with your original expression, x squared over x squared minus 1. All right, so there's one example of a partial fraction decomposition of an improper rational expression. Let's try another one. Write the partial fraction decomposition of the improper rational expression. Again, this means that the degree of the numerator is greater than or equal to the degree of the denominator. So here, the degree of the numerator is 3. The degree of the denominator is 2. We need to begin by completing polynomial long division. We put our dividend, x cubed plus 2x squared minus x plus 1, inside of our long division box. Our divisor, x squared plus 3x minus 4 on the outside. We determine, what do I have to multiply x squared by to get x cubed? Well, to multiply x squared, I can multiply x squared by x and get x cubed. We put an x up top. We multiply down to each term in our divisor. That gives me x cubed plus 3x squared minus 4x, and we subtract vertically. X cubed minus x cubed, those are going to cancel out. 2x squared minus 3x squared gives me negative x squared. Negative x minus a negative 4x, that's going to be adding 4x, gives me 3x, plus 1 minus nothing gives me a plus 1. Negative x squared plus 3x plus 1. Now we look to see how many times does x squared go into negative x squared. What do I have to multiply x squared by to get negative x squared? Well, that's going to be negative 1. We put a negative 1 up top. We multiply it down to each term in our divisor, leaving us with negative x squared minus 3x plus 4, and we subtract vertically. Negative x squared minus a minus x squared, those are going to give us 0. 3x minus a negative 3x, that turns into addition. That gives us 6x. And 1 minus 4 gives us negative 3. 6x minus negative 3. Now notice, x squared does not go into 6x. That tells me that 6x minus 3 is our remainder. And to write our solution to this division, we have x minus 1 plus our remainder divided by our divisor. Okay, x cubed plus 2x squared minus x plus 1 divided by x squared plus 3x minus 4 equals x minus 1 plus our remainder, 6x minus 3 divided by our divisor, x squared plus 3x minus 4. And once we have completed the long division, we want to decompose this fraction now. Decompose the fraction. Okay, here's the fraction we're working with. We can now factor the denominator. The denominator in this case factors into x plus 4 times x minus 1. We have, again, distinct linear factors. This is going to decompose into a over x plus 4 plus b over x minus 1. To get rid of our fractions, we multiply by the least common denominator. That would be x plus 4 times x minus 1. That leaves me with 6x minus 3 on the left-hand side of the equation is equal to a times x minus 1 plus b times x plus 4. All right, make note of the values that end up canceling out. We can expand this now. ax minus a plus bx plus 4b. We group our like terms, group our x terms together, group our constant terms together. We have 6x minus 3 equals ax plus bx minus a plus 4b. And that allows us to factor out a common factor of x from these first two terms. 6x minus 3 equals a plus b times x minus a plus 4b. Well, in order for this to be an equation, the left-hand side must equal the right-hand side. On the left-hand side of the equation, the coefficient of x is a 6. I have 6 x's on the left. That means I must have 6 x's on the right. The coefficient here must be equal to 6. A plus b is equal to 6. There is my first equation. The constant on the left-hand side of the equation here is negative 3. This quantity, negative a plus 4b, is going to generate the constant on the right. Notice there is no x associated with it. That means that this entire quantity, negative a plus 4b, must equal negative 3. And what did we just create here, fellas? A system of equations. A plus b equals 6. Negative a plus 4b is equal to negative 3. Now, I think the easiest way to solve this system of equation is to use elimination. Notice we have opposite signs of a. So if we combine these two equations using addition, notice a plus negative a, those are going to eliminate the variable a, the unknown a. b plus 4b gives me 5b is equal to 6 plus a negative 3 is 3, meaning b is equal to 3 over 5. And now that we have b, we can back substitute it into this equation here, giving me a plus 3/5 is equal to 6. And to solve for a, I subtract 3 over 5. 6 over 5, if we get a common denominator of 5, 6 over 5, that's the same thing as 30 over 5. 30 over 5 minus 3 over 5 gives me 27 over 5 for my value of a. And now that we have a and b, we can write our final answer. Again, always start off with the original expression. X cubed plus 2x squared minus x plus 1 over x squared plus 3x minus 4 is equal to, don't forget, in our first step of long division, we had this x minus 1 plus, and then what did our fraction break apart into? Well, the fraction broke apart into 27 over 5 over x plus 4 plus 3 over 5 over x minus 1. Now, this is almost the final answer. Again, we have these complex fractions. We can move these 5s to the denominator of each one, giving us our final answer, x cubed plus 2x squared minus x plus 1 divided by x squared plus 3x minus 4 equals x minus 1 plus 27 over 5 times the quantity x plus 4 plus 3 over 5 times the quantity x minus 1. Okay, so there is your partial fraction decomposition of improper rational expressions, meaning the degree of the numerator is greater than or equal to the degree of the denominator. And that just means we need to start off by completing polynomial long division first. And then we can decompose the fraction.